This podcast is intended for investment professionals only. All investing involves risk.
Hello and welcome to L&G Talks Asset Management. I'm Alastair Stewart, the Head of Investments for Venture Capital, and we're here today to demystify quantum computing. We've all seen it in the news, we've all heard about it, but what are the facts that we as investors should be thinking about? We're here today to talk about what we believe will be its true commercial scale, what we think we need to do to unlock it, and importantly, when we think it's going to happen. I'm delighted to introduce my panelists, Dr. Alessandro Curioni, Dr. John Morton, and Chloe Hall. Let's start with some short introductions. Alessandro.
I am Alessandro Curioni. I am responsible for corporate research in Europe, Middle East, and Africa for IBM, and I am a computational scientist by training.
Hi, I'm John Morton, a professor at UCL, and I'm a co-founder of two UK startups in quantum computing, Quantum Motion, which is developing quantum computing hardware, and Facecraft, which is developing quantum algorithms.
Chloe.
So I'm Chloe Hall. I'm a senior investment manager at L&G. I focus on deep tech venture capital, and that means supporting startups that are grounded in world-leading technologies, including quantum technologies. And previously, I've worked quite closely with two quantum computing companies, Quantum Motion and Oxford Quantum Circuits.
Thank you. So to kick us off, John, perhaps you could explain what is quantum computing? Why is it different to normal computing?
Sure. Well, in a nutshell, a quantum computer is the most powerful computing device that we can conceive of building based on the laws of physics as we know them today. And so what that means is a quantum computer is not just more powerful than any supercomputer we have today, but it's also more powerful than some future versions of that computer. And that seems pretty remarkable, right? It's one thing to say we can envisage a machine which beats any supercomputer today, but how can we make predictions about what such computers could do in the future?
And what can't it do? So everyone looks at AI, and AI is apparently going to solve all of our problems. Is it the same with quantum, or are there things that it's good at and not so good at?
Yeah, I mean, a way to think about a quantum computer is how we think about general purpose machines. So we call today's computers general purpose computers, but actually they're not. Alan Turing came up with this idea of a universal computer, and that's what we think about as computers today. But then David Deutsch, a professor in Oxford in the 1980s, realized that actually they're not. There's a more general form of computer that uses the basic laws of quantum mechanics. And that means that there are whole sets of operations that today's computers can't do. They're kind of a locked down version of this more general machine, the quantum computer. So what we're trying to do effectively is find this unlocked code for computers to develop a real universal machine, which is a universal quantum computer.
And Alessandro, if we think about where that's going to be most impactful, what are the kind of challenges that's going to solve? What do you see?
As we have just said, quantum computing is opening a new way to abstract reality and to represent information that is complementary with respect to what we are doing before. And there are certain type of problems that with the old way of representing information and doing computing, we could not do it. Which are these problems? They're not, problems that are not important or they are only in science, are very big problems. For example, doing global optimization of processes with many variables, like we do have in the financial services industries or in the logistic, or simulating nature in details that allow us to do better drug design or materials development, or eventually even using it, this new quantum computing technology, to analyze small but very complex data. And the important things, as I was saying at the beginning, is that we are living a time in which the new artificial intelligence and quantum computing together are going to open a full new world of possibility in algorithm research. Having the possibility to rethink the way we abstract our world and we compute on it, will allow us to do things that we could not do before.
And how are people going to access quantum computing? Is it going to be on our phones, or on our laptops at home? How do we think about that?
Well, I mean, when I first started working in this field, and I've been working on quantum computing for over 20 years, the quantum computing technology that we and most people working on requires really low temperatures, and so we were asked, well, how are you going to fit all of this technology into your phone? But of course, what's happened over the years since then is that we have been our smartphones have been seamlessly integrating in the cloud. Every time you ask Siri or your chosen AI assistant, a lot of that work is being sent off remotely. And so in the same way now, there are prototype quantum computers being developed all around the world, and they're accessed in many cases through the cloud in a seamless way. You could use your smartphone or whatever device.
By the way, it's not only a question of technology, right? Mm-hmm. But it's a question of the use cases and the return of investment to the businesses. The same way standard computing went from only on-prem to now 90% on the cloud. Quantum computing starts from that point, and that is why most of the quantum computing cycle today are going through the cloud. It's more easy to assess and the sustainability than can I have these devices in my room. Of course, as with the standard computing, there are reasons to have this device on-prem, right? Like if you want to be very secure that your data are fully controlled by you and there is no way that somebody else see it, having an on-prem system is always the best way to do, right? But in most of the cases, through software and through the cloud delivery models, you can access quantum computers, and we will be able to access quantum computers. And
you just again, I'd like to talk a little bit more about use cases. So, it can work in a number of different areas, a number of different industries. We talked about healthcare, almost cybersecurity, infrastructure, some of these areas. Where do you think it would be used first or have the most impact, and why all those areas adopt it first?
So you can go back, this is my point of view, to the type of algorithm that this technology is going to drastically accelerate, reducing the complexity of the algorithms and the broader applicability of these algorithms. So go back to classes. Optimization and global optimization is a set of algorithms and associated with many use cases, as I was telling you before. Anytime you need to optimize a complex system with many degrees of freedom, you can take advantage of this technology. And this, can really change the business in this type of industry. Think about financial services. If you are able to optimize your portfolio in a continuous way, only 1% better than others, you push everybody else out of business. And that is very broad, right? So that is why I would say that optimization, it's one of the key and broader algorithms and use cases. But second, think about simulating nature, materials, drugs, chemistry. I would say that 95% of the problem that we do have in the world, going from climate changes to healthcare, are impacted by this. Yeah? So simply to give you big classes.
Yeah, I mean, I would say my perspective, looking at the applications, you can relate all the way back to Feynman, who in a sense came up with the first applications for quantum computing when he said that nature isn't classical, damn it. And if you want to build a simulation of nature, you'd better make it quantum mechanical. So he already realized in the 1980s that in order to accurately model how chemicals, materials, drugs behave, you needed a fundamentally different type of quantum computer, one that could think in the same way that these quantum systems behave. And I think there's really no limit to the kind of applications once you consider the importance of materials chemicals, of drugs. It's not about making some problems run faster in that sense. It's simply using computers for things where we don't even try to rely on them. So if we can ask a quantum computer, can you make this solar cell more efficient? Can you make this battery charge more quickly, or use or remove a reliance on mined chemicals from this geography? Can you design a personalized medicine for this rare disease? That can really sort of transform and accelerate the way that we discover these kinds of materials, chemicals, and drugs. But then on the logistics side, already maybe sort of 15 years ago, I became aware of companies like Ocado being interested in quantum computing. And I thought, why is the company which is delivering my groceries interested in quantum computers? And it's exactly around the pervasive nature of and importance of logistics. If you have optimization problems, which can be simply expressed but have significant value to your business, quantum computers can potentially find a more effective, more efficient solution. And the way to think about quantum computers, in a sense, it's not about big data. It's about small data, big compute, where you have a problem. It's got a handful of variables, but there's so many different possibilities. It's hard for computers to compute that space, and that's where quantum computers come in. They can traverse a much larger computational space to find the most efficient answer.
So this is really a paradigm shift. Is that fair? Is this what would you compare this to? Is this the first computer? Is this the internet, AI, or is this something a bit different?
To me, it's more than a paradigm shift. And I will say that if you take what is happening in quantum computing and what is happening in AI in this decade, I will see that there were only two other big shifts or revolution in the past of IT. One was the transistor and then the microprocessor, right? And the second one was the internet. There was nothing, in my opinion, more transformational than these two. And quantum computing and the new AI together will have the same, if not larger impact. Why? Because the first two happened one after the other, and was one the consequences of the other. These two things are happening in the same decade, and so the synergies are all to be discovered.
Another way to think about how much of a paradigm shift this is, look at the computing devices that we've used. You can go back thousands of years to find these astrolabes, these mechanical devices. You can look at Charles Babbage's analytical engine sitting in the Science Museum in London. Look at the ENIAC machines based on valves that put humans on the moon, and you can look at the supercomputers today. They're all the same machine. They're all classical computing devices. Quantum computers are different from all of those, and that's what makes them so exciting.
Excellent. And now bring it back to today. So we see these announcements about different progression points in quantum computing. What do we really have today, and what's still to fix or to move forward in order to realize some of the challenges and opportunities you've talked about?
So we are creating a new industry. And we do have today machines that are they developed enormously in the past few years. And today they start, of course, to deliver value. And from our viewpoint, when I say our viewpoint, I mean IBM viewpoint, we do believe that we are going to have a first real quantum advantage. So when a quantum machine, is able to do something that a classical computer alone cannot be done, but in a provable way, okay, in 2026. And transformational impact. So when you get eventually to fault-tolerant quantum computers in 2030, 2029, 2030. But, it's not only a question of system or hardware. It's also a question of software. It's a question of integration of these machines with the classical computers. It's a question to develop probably a new quantum software industries that has to happen at the same time that these machines are going to mature. And this is happening these days. So that is why the opportunities are enormous.
Yeah. And John, you founded companies both on the hardware and the software side. Just interested in your thoughts on that.
Yeah, so in order to bring about this this reality of transformative potential of quantum computers, you have the quantum hardware needs to get sufficiently powerful, and the quantum algorithms need to get sufficiently efficient. And there's been amazing progress on both of those fronts over the past few years. The quantum computers have got at least 100 times more powerful over the past 8 years, based in terms of the number of operations they can perform. But in the quantum software space, there have been amazing efficiencies. Some of the materials simulation algorithms have got over 1 million times more efficient through, for example, the algorithms developed by Phasecraft. And so these two curves, if you can imagine them, are at the point of overlapping. So that we can realize this quantum advantage, where a quantum computer can outperform any of the best methods that we have today at solving interesting problems. And I completely agree. I think it's very exciting that this is sort of now, let's say, months away rather than years away. But we've also got to temper that excitement with the understanding that developing this really universal, error-corrected quantum computer that can address the wide range of applications that we're talking about, that's still something that most people would put towards the end of this decade or thereabouts.
And by the way, the opportunities, when I was saying a word of opportunities, you have opportunity in the applications, in the use cases. You have opportunities to create new, as we created the Silicon Valleys, in the 60s, 70s, to create quantum valleys on software, because there is a full world. But then there is a third category of value that is a full supply chain. Once you create and you build this system at scales, the technology is different, so you need a lot of different technological innovation to come in to bring them to the next phase. So from a point of view of business, you have application, software, and supply chain. That is quite unique, difficult to find in an IT, something that change everything from the top to the bottom of the value chain of the business.
And I think the interesting thing about that software layer is, and that ecosystem, is that there's such a broad range of different ways that people are currently trying to build quantum computers. It's in a way, it's a bit like computing in the 1950s, where you had, mercury delay lines and magnetic tape and valves, and the silicon chip, of course, hadn't even been invented. So there's currently lots of different ways to build quantum computers that can be accessed through, in many cases, a common software layer. And they each have different advantages and disadvantages. And it's exciting to see which of them are going to then go on and scale as their performance grows. But I think one key aspect to develop quantum hardware is thinking about the different use cases and the different costs involved. So there are some extremely high value problems to which extremely expensive machines taking up a sort of large part of an HPC facility merit that. But there'll be other sort of, let's say, lower cost but very pervasive applications for which we need smaller footprint, lower cost machines. And we've seen that in the development of today's computers. The smaller and the more cost effective they got, we got them into more people's hands, more applications were developed, and then that in the end gave birth to the impact that we've seen on computers today.
So we have a number of different solutions or technologies that are all aiming on the hardware side or aiming to build quantum computers. So your view is that multiple of these technologies would all make it through, or do we think that some will win and some will lose? Interested in your thoughts.
From our side, we do believe that the technology that we have bet on in this time frame, right, is the one that have a series of characteristics to adapt much better to the generality that I was telling you before, and really to the ability to integrate classical with quantum, right, to create what we call quantum-centric supercomputers, okay, that have a broader applicability. This doesn't mean that, as you were saying, there are not very selected and interesting applications, mainly in the scientific fields, where different type of technology could make a difference and would make sense. And by the way, the future is open. We need to invest and develop on what we do believe is going to make the largest impact in the next 5-10 years, and then be able also to change and adapt if something else come out.
Yeah, no, I completely agree. I think there's still several more years of this phase, not just because we don't know which hardware modality is going to win out in the end, but because they can be they have different strengths. I mean, I think eventually at a sort of very mature stage of the quantum computing industry, things will begin to narrow down, but that's the sort of 10 to 20 year vision. And for now, there's still so much we're learning from these different approaches that it's important that we fully explore them. My one of the approaches that I'm most interested in, which Quantum Motion is developing, is based around the silicon chip. So it's asking the question, can you take the same technology which goes behind the chips in smartphones and laptops and use that to develop quantum computers? It's an ambitious question. But if it's one where if it works, potentially it can scale to very large numbers and be a sort of long-term platform for quantum computing.
Okay. And we talked about the ecosystem and the multiple areas of the supply and value chain that need to develop, not just hardware and software. So which of those other areas do you see a lot of effort going into? Where are the gaps? Just again, people are looking at investing in the whole area. Just maybe touch on some of those other sort of parallel parts of the ecosystem.
Of course, it depends on the technology, but if you think superconducted-based quantum computers, of course, you have the technology around the chip, and there is a lot of making the chip more reliable and scale. So it's a lot of packaging related, right? Attached to this, there are the cryogenic systems, because also there is a lot of efficiency that you can gain if you do the things right. And when I say cryogenic system, it's not only the system to cool the machines, but also to do all the cabling, right? So you have all the cryoelectronics that goes in these systems. That is super important. But then, once you have a system that is integrating and is big enough, you need to start to connect the different quantum systems like we do with the normal computers to create a quantum internet. And there you have all the technology that allow to connect in a quantum way, a quantum computer with another quantum computer. So all the connectivities goes attached to. So it's really a big world. Only to speak about the hardware. Same things if you look at the software. I told you before that there is now this convergence and synergies between AI and quantum, but you represent the information in a different way. So what is the best way, once you compute an information that is represented in a different way to bring that together? There are big questions that go from the algorithm, but also to the software that you use to manipulate this information.
And I guess this is partly why we're seeing increasing amounts of collaboration. No one company, even very large, I guess, can do everything. And just how do you see that evolving?
I mean, I think that will continue to evolve as the quantum computing ecosystem develops, just as we've seen with conventional computing. I think what's interesting is trying to understand what lessons can be learned from classical computing and which ones perhaps can be misleading. For example, we need software interfaces and to these systems. We need new algorithms, but at the same time, we need to make the algorithms as efficient as possible. So things like operating systems and anything that adds extra complexity and takes the algorithms further from the hardware, in my view, is too early. Right. So people developing quantum algorithms want the lowest level access to be able to control the hardware, a bit like sort of writing in assembly code in early computers. So absolutely, the ecosystem and supply chain, it's very diverse. There's lots of collaboration, and we need to think carefully. We need to remember where the quantum computing industry is today, and what are the key problems to understand how best to develop those collaborations.
Yeah. And to add on this, another lessons that we should remember from that time is the one that once the key technology, base technology that started to be used in computing became mature enough, most of the value and the money generated was not coming from the technology itself, but for everything around this. And that is, I'm saying, because I do see a lot of efforts today in the core quantum compute technology, so the computing ones, but not enough, in my opinion, on everything surrounding that. And probably most of the value is going to be there and not here only. So to have a more balanced view on what is going to be the future of computing, it would be very, very wise for everybody. Today, the largest companies in the world in computers, so-called hyperscalers, all the value come from the top part, not the lower part that is a little bit more commoditized, right?
Yep.
Yeah, it's a really fascinating question. Of course, I'm conflicted with a foot on both camps in hardware and software. But I completely agree. In the end, that's where the ultimate value will come from. But building quantum computers, building the hardware, is extremely hard work and
for sure.
and expensive. So on the one hand, they don't exist, right? Without suitably powerful quantum computers, none of these revolutionary quantum algorithms, quantum software is able to run. So I think there's a very strong interdependence.
Yeah.
It is more expensive to develop hardware, so it's natural to see more funding flowing into there. But I completely agree that both of these need to move forward together.
Yeah, and I probably also agree that in the past few years there has been a huge focus on the first and not the same focus on the second. I'm not saying that the first needs to disappear, but that one has to look more if one is interested, in value creation, and of course is a bet that you do, and early adopters and people that have the new ideas now probably are the ones that are going to monetize in the future.
So it's a really enormous opportunity, and we really scratched the surface, but there's lots of other areas also coming up around it. Chloe, maybe, again, we as L&G and the venture team have a focus on universities particularly, but just what areas or how are people getting exposures to this industry in the investment world?
Sure. So at L&G, we'd like to get exposure to a broad range of quantum technologies at different points of the value chain, the supply chain. We'd also like to support different approaches to building quantum computers. And we're doing that through our holdings in the university spin-out funds like Oxford Science Enterprises, Cambridge Innovation Capital and Northern Gritstone. We've also made a direct investment into a post-quantum cryptography company called PQ Shield because we believe in the near-term opportunity of helping companies to prepare for the advent of quantum computing and the subsequent vulnerabilities in classical cryptography systems. But there are public companies that are exploring quantum technologies too. So the likes of IonQ and Rigetti, and also tech companies like Google and IBM. And then many private companies that are developing quantum technologies, much like Phasecraft and Quantum Motion, we do think that there will be quite a lot of consolidation in the space over time. Recently, Oxford Ionics was acquired by IonQ for $1 billion. And that really highlights the superiority of UK research in how its potential for being translated into a commercial success.
Next question. If we think about quantum computing in the context of an international sense, where do we see the pockets of technology emerging and also funding? So how is government supporting or interacting in this development?
Well, the UK has been a fantastic place to develop quantum technologies. There's been a quantum technology program going back since 2014, supporting early development of quantum hardware and some of the applications. And then most recently, the UK established this National Quantum Computing Centre in Harwell, which has begun accepting different quantum computing prototypes to deploy them and begin testing them. I'm very excited that earlier this month, Quantum Motion delivered its first testbed quantum computer to the NQCC, and the quantum processor unit, the chip that powered the device, was built on the same silicon technology that goes inside smartphones and laptops. So I think that's a really exciting step in the development of these silicon-based quantum computers.
And international collaboration is even more important because, as we were saying before, there is a strong synergies between hardware, software, application, and algorithm development. So larger is the ecosystem of possible users and researchers that are collaborating to push the boundaries, better it is. To give an example, in our IBM quantum network that we created a few years ago, we have now more than 600,000 users that are using the machines, giving feedbacks and help to develop next generation algorithms.
Final question. What and when do you think will drive the big bang moment that we've recently seen with AI, but in quantum computing?
It's a fascinating question. There's when ChatGPT hit, of course, that opened a lot of people's eyes to the power of AI. But there have been multiple big bang moments along the way, and if you wait for that ChatGPT moment, whether you're an investor or a member of a board, it's probably too late. You have to go back, maybe look at when IBM's Deep Blue beat Garry Kasparov at chess. Look at DeepMind's AlphaGo. Those were key big bang moments that ultimately led to the kind of phenomenon of ChatGPT. So I think what's interesting thing, well, what are the moments in quantum computing that take us along that path? One, I think we've already had with Google Sycamore chip and the quantum supremacy demonstration. So showing that at least on a sort of toy problem, a game like chess, you could outperform the best supercomputer, and subsequent demonstrations since then in that vein. The next one is going to be this quantum advantage moment. That's the one where a quantum computer can outperform the best computing technology at the kind of problem that matters, showing a potential application. And that, I think, we agree, is very exciting. That's probably months away from being able to showcase that, and then that leads through towards something that where we really see quantum computers begin to pop up everywhere, addressing a wide range of different applications and sectors. That's probably something around 2030. But as I said, if you wait until that moment, it's probably too late.
Yeah, I do agree on if you wait to that moment is going to be too late, because the early adopter advantage here is going to be enormous. And there is a lot of things that one can do from now to that moment. 2030, definitely going to be when we will have really the first full error-corrected quantum computers that will allow really to implement the vision of quantum computing. And so at that point, if you have an application that where you bring advantage and create really value for a business, every time you add a new qubit, you double the space and the power of the machine. So The problem is that why you cannot wait? Because this is probably the first exponential technology in computing. So it's not something that you can simply say, I wait, and then when create value, I start to invest. Because the others at that point, they are going to push you, a factor 2 away every day. Yeah.
There we are. The time is now, and it's a huge opportunity. Thank you to my panelists, Dr. Alessandro Curioni, John Morton, and Chloe Hall. Thank you.